Okay, so here we have the equation y equals 2x squared, and we are going to graph this equation without doing any table of values or plugging any numbers in for x. So the first thing we need to do is identify the vertex of our function. Now remember, back in the vocabulary section, I just pointed out to you and reminded you guys that vertex form is y equals a times x minus h squared plus k. So if there's nothing being added or subtracted to the x and nothing being added or subtracted at the end, then our vertex here is 0, 0. Now notice we have this a value here. So we need to identify that the a value is 2, and that is going to cause our graph to either shrink or stretch. We're going to talk more about that after we see the graph. The last thing we want to do is identify that this a value is a positive 2, indicating that our graph is going to open up. So let's start by putting our vertex at 0, 0. Let's go ahead and sketch our axis of symmetry through the vertex and write the equation x equals 0 for the axis of symmetry. Now from here, we have to use our graphing pattern to find the next few points. Now we know that the graphing pattern of the parent function is 1 over 1, 4 over 2, 9 over 3, etc. But now, because we have this a value of 2, that graphing pattern is going to change. So we have to multiply each of our graphing patterns by 2 to figure out the distance we're going to move from the vertex. So if I start with my 1 over 1, I have to multiply this first by 2 because that is the a value of our function. So if I multiply this by 2, remember that's over an invisible 1. And so when I multiply this out, that now gives me 2 over 1. The next movement in our graphing pattern is 4 over 2. But now again, I have to multiply that by 2. So that is going to tell us for our second movement, we're going to move up 8, but still over 2. The over number is never going to change. And the third one is 9 over 3. But again, we have to multiply that by 2 over 1. 9 times 2 gives us 18 over 3. And that's our third movement. Now we're going to put, like I've told you guys before, as many points as we can that will fit on this graph. So our first movement is up 2 over 1. Remember, over is always in both directions because that axis of symmetry gives us a symmetrical graph. Back to the vertex, our next movement is up 8 over 2. And the third movement, 18 over 3, is going to put us off the graph, so we're not going to worry about that one. Now I'm going to go ahead and connect these points to sketch my parabola. Now notice that this graph is significantly narrower than our parent function. Our parent function, let me just kind of give you an idea of what that would look like. Our parent function would be here. So this graph is narrower than our parent function. Now this is what we call a vertical stretch. This is what's called a vertical stretch. When our graph is narrower than the parent function. So that vertical stretch gives us that narrow graph. Now, why did this happen? Why did this happen? This is our a value. Our a value is 2. So we're going to come back to this, the fact that a equals 2 gave us a vertical stretch. Now, real quick, before we move on to the next one, some toolbox items. What did we do here? Identify the vertex, identify the A value, determine if the graph opens up or down. Because our A value is not 1, we now have to multiply our graphing pattern, our 149, by that A value. So we multiplied our graphing pattern by 2 to find our new graphing pattern. And then from there, we can graph our function. Okay, so let's take a look at this one. Same thing, same toolbox items. First thing, identify the vertex. Well, nothing's being added or subtracted, so our vertex is at 0, 0. Our A value here is at 1/2. So that's going to change our graph somewhat. That's going to change our graphing pattern. This graph will also open up because our A value is positive. So from there, we want to take our graphing pattern and we want to multiply it by our A value. Now here's where it gets a little bit tricky. We're not going to multiply this whole fraction by 1/2. We're only multiplying the numerator by 1/2. So if we multiply 1 times 1/2 gives us 1/2 or 0.5 over 1. Let's do the same thing here. 4 times 1/2 over 1. 4 times 1/2 gives us 2 over 2. And the last one, 9 times 1/2 gives us 9 over 2, or 4.5 over 3. And let's do the next value as well. The next one would be 16 over 4. So let's multiply that by 1/2 over 1. What does that give us? We might even be able to do more. Let's see what this looks like on the graph. 16 times 1/2 is 8. Movement over 4. So our vertex is at 0, 0. Our graph is opening up, so we're going to use our graphing pattern in the upward direction. Let me go ahead and draw my axis of symmetry. Again, this is at x equals 0. That yellow is a little bit difficult to see, isn't it? So from the vertex, we're going to use our first movement, which is up 1/2 over 1. Going back to the vertex, we're now going to go up 2 and over 2. Back to the vertex, we're now going to go up 4 and 1/2 and over 3. So 1, 2, 3, 4 and 1/2 over 1, 2, 3. And then we included this one, so we're going to go up 8 and over 4. So how does this graph compare to the parent function? Well, let me put that one on here again. So if I include the parent function, that's going to be here in green. And so this graph is wider than the parent function. This is what we call a vertical shrink. Vertical shrink. I know it's kind of weird, but the way to think about it, and I'm going to show you in the next Zoom meeting, is if you take a rubber band and you put it around each of your pointer fingers and you pull up on it, you're stretching the rubber band. And it's making your rubber band more narrow. Well, if you take your rubber band and then you push your fingers together, you're shrinking the distance between your fingers, and that's causing your rubber band to get wider. So that's one way to remember the shrink or stretch, the vertical shrink or vertical stretch. And the shrink causes your graph to appear wider than the parent function. So just real quick to make a couple of connections. We saw that the narrower graph caused a vertical stretch. And this happened when A was equal to 2. The wider graph, which was a vertical shrink, happened when A was 1/2. Now, when you think of these numbers, I want you to think about the absolute value of these numbers. We're not concerned about the fact that they're positive or negative or anything like that, because remember, the negative simply causes our graph to reflect across the x-axis. But when our A value here, the absolute value of our A value, is greater than 1, that's when we're going to have this vertical stretch happen. So if you have an A value of any number greater than 1, it's going to cause a stretch. So 2, 3, 4, 5, etc. But even 1.25, 1.5, 1.75, any value that's greater than 1 is going to cause your graph to stretch. So conversely, over here, we had a fractional value. But I use that term loosely because those numbers I just mentioned over here, 1.25, 1.5, those are actually numbers that we could express as fractions as well. But this actual value is between 0 and 1. So when the absolute value of your A is between 0 and 1, so maybe 1/3, 1/4, 1/2, 5/8, anything that's between 0 and 1, that's going to cause your graph to have a vertical shrink, which is when your graph appears wider than the parent function.